Space friend, I'm just here to have a friendly chat with you today because I think I'm going to take the day off from repair work. Wait, I'm getting a new transmission on this receiver I recently rigged up to convert binary tones into plain English. Looks like my receiver is still translating the binary code. Let me show you how I put this together, and hopefully by the time we're done, the code will be properly converted. For this project, we're going to use two Arduino boards to talk to each other using a buzzer and a microphone module. The transmitter Arduino will play beeps using a buzzer. Each beep means binary 1 and each silence means binary 0. This will transmit an encoded message to the receiving Arduino as sound. The receiving Arduino will listen for the beeps with the microphone module and read the sound levels with analog read. It will decode the beeps into binary and then print out the message onto the LCD. We need two Arduino boards, a microphone module, a buzzer, an LCD, and 11 jumper wires, all but one male to female. First, we set the buzzer pin to pin 8 and set the buzzer tone's frequency. You can play around with this value and set it to whatever you want. I just found 500 to be the least annoying. The bit duration means each bit, whether it's a 1 or a 0, will be transmitted for 400 milliseconds. The gap duration states that there will be a 50 millisecond pause between each bit to separate them clearly. This code took quite a bit of trial and error to get to work, and I only succeeded after I added a preamble. This preamble helps the receiver sync to the start of the message so that it only starts translating the binary code after it hears the preamble. The rest of the string makes up the binary code that we're going to send to the receiving Arduino. In the setup, we set the buzzer as an output and wait for 1 second to make sure that the receiver has had time to start up. In the loop, we initialize I to 0 and state that while I is less than the length of the binary message variable, increase I incrementally by 1. The bit variable of type character retrieves the character 1 or 0. Char@at is a method built into Arduino whenever you're using the string class. It returns a character at a specific index. For instance, binary message.char@0 returns the first character. If the bit is 1, then we use the tone function to play a 50 Hz sound like we specified earlier, and if the bit is 0, then it just stays silent. Delay waits 400 milliseconds to transmit the bit. No tone ensures the buzzer is turned off afterwards. And then delay waits 50 milliseconds before moving to the next bit. We're then going to delay by 5 seconds before the message is repeated. First, we include the necessary libraries to use the LCD as well as create an LCD object. I'll link a video at the end of this one to explain how LCDs work if you want more detail on that, as well as include a link in the description to the specific LCD that I'm using. We set the microphone to analog pin A, and then we create a variable to store the number of analog readings to take for each sound sample. Analog microphones produce noisy, fluctuating signals, so just using one analog signal can be misleading due to electrical fluctuations, background noise, or sudden spikes. So instead, we're going to take multiple readings and then average them to smooth out the noise so that we get stable, reliable readings. With the threshold variable, we're stating that if the average mic input is above 100, then it is a 1 bit, otherwise it's a 0 bit. You may have to play around with this to fix your threshold if this isn't working for you, but after a lot of trial and error, 100 is the value that worked for me. Unsigned long is a data type that's used for storing large positive integers. Unsigned allows positive numbers only, and long stores larger numbers than int does. Bit interval controls how often a new sound sample is taken, and here we're saying 450 milliseconds. Last read time is going to enforce that using millis. The binary message variable is going to store the received binary bits. A Boolean variable is either true or false, and we're going to set the preamble detected as false to start. It'll become true when the message 1111 is found, like we set up in the transmitter code. We're going to add some animations to the LCD, so effects done is being set as false to start. In the setup, we start the serial monitor, initialize the LCD, and print listening. The first line of this if statement in the for loop is stating that it's going to run every 450 milliseconds based on the time since last read. We start the total at 0, initialize I to 0, and while I is less than the sample count, increase I incrementally by 1. The plus equals operator is shorthand for adding something to a variable and then saving it back to that variable. It's equivalent to total equals total plus analog read mic pin. So we're adding each read from the microphone to the total variable, and then we'll get the average by dividing the total by the sample count. This is to get the average sound level like we discussed earlier. The bit variable is using a ternary operator, which is a shorter way to do an if-else statement. We're first doing a comparison of if the average sound level is higher than the threshold, then if true, use 1, and if false, use 0. We could do an if-else statement to achieve the exact same result, but this is cleaner with less lines. The exclamation point before preamble detected is a logical not operator. It's stating if the preamble is not detected, then run this part of the code because we only want to start recording the real binary data after that 1111 is detected. Then it'll set preamble detected to true and then not run this part again. We reset the binary message so that we can start clean after we've detected the preamble. The else block runs when the last 4 digits are not 1111 yet. The purpose is to keep only the last 4 bits in the binary message string, discarding older bits that are no longer needed for detecting the preamble. Otherwise, the bits would just keep appending forever and make binary message longer and longer, making the process potentially slower and taking up too much memory. After we do receive the preamble, we wait until 32 bits or 4 characters are received. If you want to change the binary message sent by the transmitter, you'll have to change this section 2 to account for the length of your new message. Then we call a function that we created below called print binary bytes to print and decode the full binary string. We also call other manually created functions called flicker static, signal lock animation, and display message. These are all just fun animations and a display function that we're adding. The final section before our functions is to reset the LCD and binary message variable to receive the next message. The flicker static function simulates random noise on the screen for effect. It's just going to flicker 1s and 0s on both of the rows. The signal lock animation fills the LCD row 1 block at a time to simulate a signal locking in. It prints signal lock starting at the first section of the first row since we set the cursor to 0, 0. Then we use a for loop to set the cursor to the ith section on the second row and use write to print out a specific character. This 255 is pulled from the specific LCD module's internal character ROM. You can check your LCD's ASCII table to see what other characters can be displayed for different numbers. On most LCDs, 255 is a solid block though. The print binary bytes function splits the binary string into 8-bit chunks, converts each to a character, and prints both the binary and the character. The function takes a string parameter that we're calling bin. Bin.length tells you how many characters or bits are in the bin string. Bin.substring extracts a portion of the string starting at index I and ending just before I plus 8. It takes an 8-character chunk from the binary string bin starting at position I. So for example, if bin is this and I is 0, bin.substring 08 returns this. Bytestring.cstring converts the Arduino string data type to a C-style string for C functions. That was a very hard sentence to say. It's used here because the string to long, which is this strtol function below, requires a C-style string, not an Arduino string type. The reason we're using string to long is because it converts strings representing numbers in any base to integers. It supports base 2 or binary, which is what we need for this code. The Arduino string class does not have built-in methods to convert binary strings to integers, while the string to long does. The decode binary to text function converts the full binary string into readable ASCII text. The parameters in the C variable are first the input C string to convert, so here are the binary digits. The second parameter is a pointer to a variable to store the address of the first invalid character. That's not used here, so we're just putting null. The third parameter is the base for conversion, and we're putting 2 for binary. It then adds the results to the C variable. The display message function prints alien message received, delays a bit, and then prints the message decoded from binary. Let's decode our message. Oh, it's just saying help over and over again. Ugh, do I want to be a hero? Fine. I guess I'll figure out where this signal is coming from and go save the day. Feel free to follow behind me just in case I need some backup. We're going to add some and the gap. Motorcycles in space? The space motorcycles today.